Stand on the top floor of a 500-meter skyscraper during a strong windstorm and the building moves. Not imperceptibly. Not as a vibration you might mistake for something else. The building sways, slowly, with a period of several seconds per cycle, by distances that can exceed 1 meter at the top. The floor beneath you shifts. Objects on flat surfaces slide. People who are sensitive to motion feel it clearly. And this is not a sign that something is wrong. It is the building working exactly as it was designed to work. A skyscraper that does not sway in high wind is not safer than one that does. In most cases, it is more dangerous. Understanding why requires stepping back from intuition about what rigidity means in a structure and starting with the physics of what wind actually does to a tall building. Wind does not apply a single steady force to a building. It applies a fluctuating dynamic load that varies in intensity and direction across the height of the building, across its faces, and across time. At any given moment, the wind pressure on the windward face of a tall building differs from the suction on the leeward face. It differs between the lower floors, where wind speed is reduced by ground friction, and the upper floors, where wind speed is higher. And it fluctuates, gusting, varying in intensity, with characteristic frequencies that depend on the wind speed and the turbulent structure of the atmospheric boundary layer. A structure subjected to a dynamic load responds dynamically. It does not simply deflect to a new static position and hold there. It oscillates, moves back and forth around the deflected position, at frequencies determined by its own stiffness and mass distribution. These are its natural frequencies. And here is where the critical engineering principle enters. If the frequency of the applied load matches the natural frequency of the structure, resonance occurs. The oscillation amplitude grows with each cycle. In an extreme case, resonance can grow until the structure fails. This is what happened to the Tacoma Narrows Bridge in 1940. The bridge's natural torsional frequency matched the frequency of vortex shedding from the wind flowing around its deck. Resonance built until the structure tore itself apart. The same physics applies to tall buildings. A rigid building, one with very high stiffness and therefore very high natural frequencies, would experience very large internal forces when wind loads are applied, because the structure cannot deflect to absorb the energy. A flexible building, one that can sway, distributes the dynamic energy of wind loading through displacement rather than through internal stress. The peak stresses in the structural members are lower for a given wind load in a flexible structure than in a rigid one. This is the counterintuitive core of tall building structural design. Flexibility is not a compromise forced on engineers by the difficulty of building rigid structures at height. It is a design strategy that reduces the structural demand on the building's primary load-carrying elements by allowing the building to move. The design challenge for skyscrapers is not to prevent swaying, but to control it. The building must be flexible enough for wind-induced stresses. Stresses must remain within the capacity of the structural system, without the motion at occupied floors exceeding what occupants can tolerate. We must also prevent the deflection at the top from accumulating to levels where secondary structural effects, known as P-delta effects, become significant. Human perception of building motion is the practical limit for sway design. People are surprisingly sensitive to low-frequency lateral acceleration. Motion becomes perceptible at approximately 10 millig's of lateral acceleration, which is just 1/100th of the acceleration due to gravity. The threshold for discomfort is 15 to 20 millig's. Above 30 millig's, motion is distressing and affects the ability to function normally. Designers typically limit peak acceleration at the highest floor to below the comfort threshold under a wind event occurring once every decade. While safety systems must resist rare extreme winds from a 500-year event, the comfort criterion governs the day-to-day experience of the occupants. Structural systems have evolved since the first steel-framed skyscrapers appeared in Chicago in the 1880s, which used moment-resisting frames. Moment frames use rigid connections between beams and columns. However, they become inefficient as building height increases. Shear walls, made of reinforced concrete or braced steel, are more efficient for tall buildings, resisting lateral loads through their own plane. A reinforced concrete core housing elevators provides a shear wall system that resists lateral loads with less material than a moment frame. Pioneered by Fazlur Khan in the 1960s, tube structures treat the entire perimeter of the building as a structural element. Closely spaced perimeter columns act together as a hollow tube cantilevering from the ground, maximizing the structural contribution of each kilogram. The World Trade Center used a tube-in-tube system, while the Willis Tower utilized a bundled tube system of 9 individual tubes. By terminating tubes at different heights, engineers reduce the building's cross-section, effectively managing the forces of nature. Even with optimized structural systems, very tall and slender buildings may require supplemental damping to meet acceleration comfort criteria. Damping is the dissipation of vibrational energy, the mechanism by which oscillation amplitude decreases over time after an applied load is removed. All structures have inherent damping from internal friction in materials, typically 1 to 2% for steel and slightly higher for concrete. This inherent damping is usually insufficient to limit accelerations to comfort levels in very tall buildings. Tuned mass dampers are the most widely known supplemental damping system. A TMD consists of a large mass, typically 300 to 1,000 metric tons, mounted on a pendulum or spring system. The system is tuned to the building's fundamental natural frequency. When the building sways, the TMD mass moves out of phase. When the building moves one way, the mass moves the other. The energy of the sway is transferred from the structure to the TMD and dissipated through dampers attached to the mass. The Taipei 101 Tower in Taiwan contains one of the most visible tuned mass dampers ever built. A 660 metric ton steel sphere, suspended by cables from the 92nd floor down to the 88th floor. The sphere is visible to building visitors and has become an architectural feature in its own right. During Typhoon Soudelor in 2015, the sphere swayed by 100 centimeters, reducing peak acceleration by an estimated 40%. Active mass dampers extend the TMD concept by adding a powered actuation system that moves the damper mass. An active system can respond to a broader range of frequencies and can be tuned in real time. This accounts for changes as the building is occupied, as temperatures change, and as the structure ages. Active dampers require electrical power and control systems, achieving significantly better performance than passive systems. Aerodynamic shaping of the building's exterior is another tool for managing wind-induced motion. The forces wind exerts depend on the building's shape, how the wind flows around it or creates vortex shedding. Vortex shedding occurs when wind creates alternating eddies on each side, generating lateral forces that oscillate. If this frequency matches the building's natural frequency, the result is crosswind resonance, oscillation perpendicular to the wind direction. Tapering the building profile prevents the vortex shedding frequency from locking onto the building's natural frequency. Twisting the building cross-section disrupts the organized formation of vortices. Corner modifications, chamfered, recessed, or rounded profiles change the separation point of wind flow. The Shanghai Tower uses a twisted, tapering form specifically designed to reduce wind loads. Testing showed a 24% reduction in wind load compared to a conventional rectangular form. So, why do skyscrapers sway but never fall? Because sway is the structural response that keeps them from falling. A building that cannot sway absorbs wind energy entirely as internal stress in its structural members. A building that sways absorbs wind energy through displacement, through the movement of its mass, and distributes the resulting stresses across the structure in a way that keeps them within the material's capacity. The engineering challenge is not to eliminate this movement, but to control its amplitude, limit its effect on occupants, and ensure that the structural system can sustain the forces generated by the most extreme wind and seismic events the building will experience in its service life. The building moves because moving is how it survives, and the tuned mass dampers, the shaped profiles, the concrete cores, and the tube structures are all engineering tools for ensuring that it moves in a controlled, predictable, and survivable way. Every time the wind blows, for the entire century or more, the building is expected to stand. If you're thinking about what happens when a skyscraper faces not wind but an earthquake, where the ground motion is applied at the base rather than as a distributed force along the height, and where the frequency content of the excitation is different from wind, the structural response is a fundamentally different problem, and one I've covered in another video.